Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 64. So in today's lesson, we are going to begin looking at the data structures of trees. So we've been building up the last few times, so we're going to really start getting the look at a tree today. So we'll just go ahead and begin with an example here. Let's see. I've got a workspace already created. I'm going to add a text file. All right, so we're going to have a structure that looks sort of like this. Let's do it like this. I'm trying to make this look decent. Something like this. And then we'll need some parts here. Like this. And then we can do do it like that, and let's make that one. So that we're going to do something like this, and we're going to claim this is a tree. So last time I did an example of the more formal. You have a root, and then you have the two sides. I'm going to represent it more like this here in text. I should have had one more space between these, something like that. In fact, let's put a one here just to make it a little more explicit. So the idea with a tree is you have a root, so the beginning of the tree, and notice it's reversed. You'll see memes online if you look for trees a lot of times of finding an upside down tree, and it's like, it's a programming tree or something to that effect. Or, basically, it's a rooted data structure, though. So you have a root that's the beginning, and then it has children, and it knows about its children. So the children are called leaves. So the top node's a root, and then underneath we have it has two children, and they are this one and this one. So the child nodes, they can have their own children, like A does here, and we can have more than two. We'll look at different types of trees and eventually as well, and you could have one with 3 or 4 or any number there. So the inner or outermost ones are called leaves, so ones without a child. So let's see. So another thing with trees is something called depth. So depth is how far you are from the root. So here the depth is, a lot of times you'll see it as or you'll see it labeled as 1. In reality, it probably should be 0. So saying this is 0, so 0 and then 1. It's basically one step from the root, though, however you want to calculate it, if root 0 or if A0. I'd probably do root 0 and then say this is level 1, this is level 2, but depends on what you're reading, you might see it differently. There's also height, and height's the largest subtree. Something like this. So something like that, and now we have a 0, 1, 2, 3, so a height of 3. So the height's the largest. So even if this one's not, the height of the tree is still 3 because there's three children. So some things to keep in mind: the root is a parent, so each one of these are parent nodes, A and B, and then A2 is now as well. So is the root. Even though it's a little special, they're still all they're still parents. Can a leaf be a parent? Probably not from how I'm going to be defining it. From how I'm defining it, I'm saying that the parents are ones without children. And then that means the ones without children are called leaves. One more important question is, can a root have multiple parents? And for our purposes, no. We're going to see that that's important for the trees. And there's other data structures that you can do where that's the case, but trees, probably not. So let's see. Let's do let's go ahead and start. Let me save this file. Let's go over here. Let's create a class. So we'll say class tree node. All right. So we'll have a public int value and a public list of tree node children. So there we go. There's just the start of our tree. So we can have let's get rid of this. We can have a tree node root. Let's set the value here. We'll set value equals, we'll do 1. And I guess we can just use the new format. So let's copy. See that move down? Not having any luck. We'll do 2, value is 2. Wait a minute. I used A, didn't I? Let's change this to string. We'll do that, and we'll say this one is A2. I guess this one's root. And this one's A. B. Something like that. And then we'll have a 4. A1, A2, and A3. Well, I thought we had A3. Then a final one. I apparently can't talk today. And then final one of A2A. That was the naming scheme, right? Yeah, A2A. Okay, so there's just created the node. So now to actually add them, we would need to add them as children. So we would do something like root dot children dot add, and then we would add node 2 and node 3. So there we go. There's just that structure. And then we would, for A, so node 2 dot children equals 4. Copilot helps sometimes, that doesn't help sometimes. So 4, 5, and 6. And then 4, get 7. So there we go. So there's just our tree. So that should be roughly this structure here. Maybe we should see if we could print that. That wasn't what I was planning on doing, but maybe that would be the good way to do it. Let's do a method here. Static void traverse. There. So let's see what happens if we just do it like this. So let's say we do this. Dot value. And now for each that's actually what I want. That. And then we'll just traverse again. So remember we talked about recursive methods. That's what we're doing here. Let's see what this warning is. We are missing a brace. Here it needs to have a value. We'll leave that. So there we go. So this is why we were talking about recursive methods. It's because that's how you usually go through a tree and you'll work through recursion. So let's just see what this prints. I think we will see that it at least puts stuff in the order we expect. So let's see what that order is. No. Oh, I did call traverse. Traverse root. It's not called traverse tree, it's called traverse. There. So let's see. So there we get root A, A1, A2, A3. That seems reasonable. But let's see if we can format it a little better. Let's do what do I want to do? Let's do let's see if we can just do this. Console.write. Now I'm thinking about this probably isn't going to work. But we'll see. I predict this is going to look bad, but yeah. I'm needing to pass it down, so I would need to pass the value of be able to say go down a level, go down a level. Let's try that. So let's say int level equals 0. Level plus 1. And now here for this, instead of that, we would do, let's see, for int I equals 0, less than level I plus plus. So now for each level, now we would add that. Let's do this. Let's do -1. -1, so we don't do the last one. So now we'll do console.write. Two spaces, and then console.write. Now we will add our thing here, and let's see if that sort of works. A little better, but not a ton better. That one I'm fine with. A1. Do we have A1 correct? We loaded on the node 2. Yeah, that's assumed is correct. So let's see what it's doing there. So let's try to fix that bug. All right, so here we've got, let me close this other terminal instance. So now we've got the root. Yeah, so let's see. I wish I could get this fit. That's not great, but that'll do. All right, so let's step through. So here we just add we just add the value. Now it added A. So now levels 1. And fell through. Maybe we don't want it to do that, actually. You can't even stop it from this angle. Instead of -1, let's see what happens if we just do it as 1. Oh, I hit my breakpoint. Yeah, that looks a little better, so I didn't need to do the extra -1. So yeah, that sort of looks reasonable, and what I'd like to do is add the spaces in there, but yeah, I don't see a good way to do that right offhand. But there you can sort of see that's a similar structure to what we were drawing here. At least roughly. I put A2 on the wrong tree though. Let's fix that. So this should have been 5 instead of 7. So now if we draw it, now it sort of looks all right. Okay, so there's just a little taste of writing a tree and doing some recursion to find the tree. So let's see. So trees give us some nice properties. So back in the sorting algorithms, we looked at different runtimes. So, sorry, my voice is trying to go out. So we looked at different runtimes though, like bubble sort was n squared while merge sort was n log n. So our trees give some nice benefits there. So with a tree, you trade off sorry, give me just a second. So with a tree, you trade off some complexity in constructing the tree. And on the other hand, you get a little bit better on actually working with it a lot of times. Let's trying to pull up something. I'm not seeing it right offhand. So let's see. So with different data structures we've looked at though, for a linked list, by the way, a linked list looks an awful lot like a tree. We have A, B, C, D. So a linked list looks something like that. And if we want to add something to the tree, what we do is we go to wherever we want to add it, and we usually how we were doing it, you would start at A and go through until you found where you wanted, which say we wanted to add something between B and C. So then we take B's next and point it to our new node, and we point the new nodes next to whatever B's used to be. So add's very easy. When we have an array, things are a little trickier with it. The way to add something to an array is you have to make a new array of the new size. We'll do it like that so I don't have to deal with them. So, and then we copy the values. We copy the new one wherever we need it. And there we inserted one. If we just wanted to insert it at the end, it's a little easier. So we just create the new array, copy the values, and insert it at the end. Stack and queue were really easy. So I don't remember how best to just do it. So we have that already on the stack. So for that, we just put an X there, and it may have to do the resizing thing. We can use a list instead and be able to do it and let it do it automatically. And we've seen that. Q works very similar to that. So a tree, it looks sort of like a mix. So it looks a lot like this, but sometimes there's a little more work. So let's say we want to add, let's say we want to add a B, let's say a B2 or B1, I guess, for my naming, for my scheme. So what we do is we go find B. So we start at the root. We say, root, where are your children? And we're looking for B. Is A the child? No. And then B, okay, we found it. All right. So add a child to B. Does it have any more? And it would get the list. If we wanted it in order, we'd have to take that in mind. But there we can add a B. If we wanted to do a C, we would say, okay, find where we want to add it. So A, B, C. Here, I'm going to delete this just so it matches what we were drawing. There, I think that matches our drawing a little better. If we wanted to do more complex, let's say we wanted to add a new one here. So something like this. So then we would do something more complex. We'd say, okay, find the root, or find the A. Search through A's children until we find A2. Search through A2's children until we find A2A. And then search through A2A's children. It doesn't have any, so then we can add it. And we add it to the list just like we did before. That's still a very quick operation, however. So what we did there is we had to go through the list. So we had to do a little bit of searching, but then we found it. And what we'll find is that it's actually log n. So let's see, let's do a little, let's open the calculator. So 1, 2, 3, 4, something like that. So let's see, let's do, do we see ln? Let's do 4 ln. Right, that's not right. 10. Let's do 10 ln. Let's see what that is. 2. So we're rounding up to 3. So 1, 2, 3. That seems about right. So there, so it's count. So, and that makes sense because what we're getting at is that it's log of n, or big O of log of n on average for adding to a tree. And we'll see that sometimes there's cases where that's not the case, and sometimes it's actually big O of n in the worst case. But for adding, that's actually pretty quick. It's not constant. It's not as fast as doing the array. It's not as fast as doing this, but it's pretty quick. And we'll look at a special type of tree next time, probably called a binary search tree. And it takes advantage of this, and it, like I said, it trades off a little bit on the insertion because you have to do a little bit more logic on insertion, but it makes this actually searching for something easier. And we'll notice here, these isn't good examples. I guess we could use this one. We talked a long time ago. Normally there's a linear search. You just search each element. If you know it's sorted, though, you can do a binary search. And binary search, you just say, okay, start in the middle, and is it higher or lower? And if it's higher, you throw away the first half and go higher, or if it's lower. And in doing so, you're cutting down the number of searches you have to make. And in that case, you're cutting it down log n, so you're halving it each time. So little bit on them. Let's see. I wrote down so for data structures, so an array, it's a linear shape, and you access it based on an index. For stacks and queues, they're first in, first out. Linked list is linear. You have to go through the entire linked list. A tree is hierarchical, and you have to traverse it. So, that's really rough intro to the basics. So let's talk about some problems that can occur. So it's really easy to get off with trees on what we talked about last time. With when you're creating them, passing around the objects, you can pass around the objects incorrectly and get your tree wrong. That tends to be what I've seen as the most common issue. Another thing, you can't just index this. Like if I pass in a index, what does that actually mean? So with an array, I could just do something like int r equals, and we can just do r of 2, and we can access it like that, and we can change it if we needed to. Anything like that. It doesn't make sense for to do it with a tree, because what does that mean? Is it the children of is it your children? Do you need to account for your children on the inside? And it doesn't make sense to do indexing. Stacks and queues are last in, first out, and first in, first out. So there's some work there. Another important point is there shouldn't be any cycles. If there's a cycle here, like say for some reason we make let's do this. Let's fill out here. Let's say node 7.children.add node 2. Make it as bad as possible, I think. So let's see what happens if we run this. And we should have turned off the display. Yeah, let's stop. Let's stop and turn off the display just a second. Let's see what happens. See if we ever finish. Stack Overflow. So what happened there? We had a cycle, so it just kept circling back and forth. We said this node here had this one as a child, so then they just kept circling and back and forth until it overflowed. So that's another problem that you'll find that's possibly easy to run into, easier than you would think. The other problems, thinking about it the other way, like what if you're at the child and how do you go to your parent? We haven't given us a way to do that. You might have structures that need that and can do that, but in general, I don't think I've actually ran into you needing to know that usually. Usually you start at the root and go down. I guess maybe there's specific reasons you would need the backlink, and then you would have a link both ways. So I guess it's possible. I just haven't needed to really do it. So let's see what else. That's actually pretty much what I had for topics. So let's do this instead. Let's add another method. So here we have our traverse. We have our tree here. Let's remove this one since we added. Let's not. Let's do this. We'll move that over here so I can keep it up and refer to it a little easier. So let's add this. Let's do a node 8. A2A 1. And now A2A, so node 7. So now node 7 actually gets something. And what else? We added a B1. So 9 B1, so that is node 3. And we need one more for a C. Just mute everything. Node 10. There we go. Let's see if that sort of looks like our structure here. Build error. What did I nuke? There we go. So now that sort of looks all right. Yeah, that looks similar. Okay, yeah. All right, so let's do a little more work. Let's say we want. Let's see what would we want to know here. So there we printed the values. Let's count the nodes. So nodes, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 nodes. We actually knew that from the numbers here, but so let's do a count. Static void count nodes. Nodes. It should return an int, I guess. So let's do this. So we would need this to be null. So let's do this. So if node is null, return 0. Else there's at least 1. So var count equals 1. So now for each that count. Let's see. So we add 1. Yeah, let's do like this. Let's do plus equals count nodes. Passing in child. Something like that. And then we need to return count. I think that might actually get us there. So what we're doing there, we're saying, okay, start the count. So we count the one we're currently in, and then we go down and check all of its children. And all the children, they add their self and then return if they have no children. So I think that will do it. Let's see what happens. So here, let's do CW count of nodes. So count nodes. Root. There. Let's see what happens. See if we get anywhere close to 10. And we get a 10. So there we go. So that wasn't that hard. So that sort of makes sense. So what I'm saying here is, okay, if there's none, we're done. But if there is something, then we say, okay, count this node, and then count, and then pass on the children and say, okay, child, give me your count. And then it says, give me, or it gets a 1 and then does that all the way down here. And then this one says, okay, I have 1. And then it returns 1. And then this one says, okay, my child, so I have 1, and then I had 1 child, so 2. And then 2 and, or it returns 2 here, and it says, okay, 1 and 2, so 3. And then, so at this point, so this one's returned, so 3. So 1, 2, 5. 6. And then they say, okay, A returns 6. B returns 1, 2. So 7, 8, 9. And then the root was 1. So that's where we get 10. And I think that makes pretty good sense. Notice it's, once again, recursive. So we're seeing a bit of recursion here. Let's see. What else could we do? If we'd done numbers, we could have found the largest value. I didn't do numbers, though, so can't do that. Let's get the count of leaves. Static int count of leaves. Node. So we'll do if that return 1. So if you have no children, you're good. Else, if there's children, for each return leaves. I think something like that will do. So here we're saying, okay, so if it's null, there's none. That means there was no tree. If there's if it's just the root node, there's 1. And otherwise, we do the same, a very similar count to what we did for count of nodes earlier. All right, wait a minute. Yeah, so here's the only way we get 1 is if there's no children. So let's see if that works. So we should be expecting what? 1, 2, 3, 4, 5, I think. And we didn't call it. Count of leaves. Let's see what that gives us. 5. Okay, that seems correct. So let's do let's do this. Let's do a static int get height. So we'll have the same if node that check. So now we want to find the height. So let's see. So to find the height, we want to do what do we want to do? We want to say starting at the root, so that's a 1. Each child inside, how deep does it go? So let's do this. So var height equals 1. So for each there, something like that. And then at the end, we'll return height. Let's see if that works. So let's see what that does. And that's, once again, forgot to do it. So let's see. So let's see, what do we expect? So we expect 1, 2, 3, 4, 5. We got a 1. Incorrect. Okay. So let's see. I guess there's never any increase. Maybe that instead, actually. See if that gives us a 5 there. It does not. Okay. So let's think about this a little more clearly then. So start at the root. So that's a 1. So for each child, we'll add another height. Maybe we just don't need that. And maybe that's the actual case. 10. No, that's incorrect. What do we want to do here? So for each one, we say, okay, give us the height. So we have your height, and then go on down the list. Interesting. I should have thought about this before I tried this one. This one's actually tricky. So let's see. So if the so height is 1. If there's no children, it's a 1. So if there's one child here, we would go in on the inside. Let's do it like this. Let's do this. So our max height equals 1 as well. And we'll be returning max height. If height is greater than max height, then we set this. Let's see if this does it. 10. Nah, it still didn't work. Okay, so let's see. So what do we want? So we know it needs to be recursive. I'm trying not to do it with a reference, because I could do it with a reference value and just pass it down, and each time you go into a loop, you add 1, but that's not what I want to do. So let's see. So 1 for each child, they have 1. So 3. 3. Here, let's do this. Let's debug just a little. Let's see what happens here. So here we get a height of 1. Value A. Let's make this a little easier. Let's do toString and return value. Make it a little easier to see there in the debug. So now if we look here, we can see it's an A. So height is 1, which makes sense. A1. Yeah, that's not doing what I wanted it to do, so let's see. So let's see. So we call get height. Here, let's think. So we start at 1. And then we say, okay, for each of these, what is your height? So the height from that position. That can just be height equals get height. And we don't even even need that. So get height. So let's see if we can get that right for branches. So let's do it like this instead. Let's get rid of that. Let's make that height. We'll get rid of this, and let's do this. Let's do a CW height. So let's see what this is at each time it reaches there. So 2, 2, 2, 3, 7, 10. It's still not doing right. So let's see. So 2, 3, 5. Yeah, it's count. Yeah, I'm just counting there, and that's not what I want to do. Yeah, I guess it's the same thing as I'm doing here. Oh, I'm going to actually look that one up. Let's see. Since we're about out of time. So let's do it like this. Yeah, so we do need a max. So here, if the count is 0, then we return 0 because there's none. That makes sense to me. So that's getting the leaves. So is it a leaf? Else, and here's where I was messing up. So let's do for each, just like below. So if let's do something like this. Maybe. And I guess, let's see. I guess we want to then return height plus 1, I think. Let's see if that's anywhere closer. Now we get a 5. Oh, that seems right. So what I was doing wrong there, I was getting the height. I wasn't returning here. So we didn't have the base case. So I was setting to 1 each time. So it was always counting rather than saying, okay, so we got the leaf. So the leaf has no additional height. So then we're done. That makes sense. So that's getting the height of the tree. So there's this little working around with trees. Get height, get a count, get a number of nodes, and actually traversing. So in next lesson, what we're going to look at is actually looking into a tree, and we'll look at building a binary search tree, or I say binary search tree, binary tree, and we'll look at different ways of traversing it. So we looked at 1 here today. We'll see that there's 3, and we're going to work through those 3 In fact, we'll probably use the same workspace actually. I might just adjust it for a binary tree, but we'll see. But that'll be the plan for next time. We'll either go ahead and pick up, continue with trees and look into binary trees. So I guess we'll go ahead and close there. So the summary is basically a tree is just a structure where every node knows what children it has, basically. So it knows what children it has, and then we have to use we use recursion to find it. You'll occasionally find programming challenges where it's don't use recursion, do the tree, and you can do that, but we're going to use recursion to make it easier. So we'll go ahead and call it with that though. So next time will be binary trees. So thanks for watching and have a wonderful rest of your day.